Okay, so we are into the last lecture on linear models for classification. We looked at linear models for regression, and then we started looking at linear models for classification. And in linear models for classification, we looked at discriminant functions. And today we're going to look at probabilistic generative models as well as probabilistic discriminative models. These terms are thrown around quite a bit in AI and machine learning, discriminative methods, generative methods. So you might as well get a feel for what those are. Okay, so that's going to be our topic for the day. Um, Let's see, let me just also mention the projects and so on. I believe project 1 is due today, and project 2, Mihir is formulating it for me to look at, and we'll have it to you out soon. Your project 2 will involve using neural networks. Project 1 was about logistic regression, right? So it's going to be on neural networks. So anyway, coming up with a good project requires some careful thought, and so that's going to be out shortly. Okay, so we will begin with the probabilistic generative models, and let me share my slides for the day with you. Okay, so we are still doing linear classification. So these models are still dealing with things like planes and hyperplanes and so on to separate classes. And okay, so what are we going to do in this particular section is overview of generative versus discriminative and so-called Bayes classifier, the terminology that comes from pattern recognition, where they say Bayes classifier is based on probability models. And then we look at continuous inputs and discrete inputs. And we go on to generalize some of these ideas to so-called exponential family. So it's actually quite a quick overview of these. So these methods for classification can be divided into generative models or discriminative models. Generative models are two-step. So it involves, in the first step, you infer class conditional densities and priors. So you would say, well, your classes C sub k, k is a subscript for the class number. And so we infer the distribution of X, whatever you're observing, under each class. So that's Px given Ck. And then the priors are how often these classes occur. That's a discrete distribution. Px given Ck could be a continuous distribution if X is a continuous vector, for instance. The priors, of course, the number of classes is discrete. So it's going to be a discrete distribution. What's the prior probability? Even before observing any input, how often do these classes occur? So we use the class conditional densities that are learned from the data and the PCKs that are learned from the data to allow us to take any input X and classify it to class CK. That's this expression P of CK given X. That is X, in this case, X is given. Say, what's the probability of the class CK? And we want this for every CK, assuming all of them add to 1. And Bayes' rule says P of CK given X can be written as X given CK times P of CK times P of X. So that's a fundamental rule of probability, which is called Bayes' rule, which relates the distributions of two variables, A and B, P of A comma B, or A given B can be written as B given A times probability of A divided by probability of, in this case, the probability A or B, that's what we're dealing with, okay? So So this would be A given B. So that would be B here. Okay. All right. So this is a Bayes theorem application, which allows us to combine the class conditional density and the prior. And in this case, denominator is the probability of X. And what is this probability of X? It can be obtained by a product of this product in the numerator summed over all values of CK that marginalizes out CK, right? You see the numerator is nothing but X comma CK. And the way to marginalize CK is to sum over all values of CK and you get probability of X. So denominator can be obtained by all the numerators. So that's a two-step approach. You need two different probability distributions. The discriminative approach is one step. We directly infer the posterior probability P of Ck given X. So we directly approach this problem. That's what logistic regression does. It calculates the probability P of Ck given X is stated as sigmoid of W transpose X. So that is directly infer that. And how do you infer it is knowing the W's. You're able to infer that value and you can just plug in sigma of W transpose X. The learning problem is how to figure out the W's. Whereas in the generative model case, we're actually determining the distributions. Decision theory is used in both cases to assign new samples to a class. So if you know the probability of the class, you can use that probability to see whether it's prudent for you to classify it like that or reject it, all right? Or we can add some weights saying how sure do you need to be to decide to go for class 1 or class 2, because if they're very close, maybe you don't want to make the decision. So interestingly, the generative model, we just said that P of C1 given X can be written as P of X given C1 times PC1. The denominator, we've expanded it out here. It's got both the terms here, which gives us P of X. And we notice that if you use A to represent logarithm of P of X given C1 times PC1, P of X given C2, PC2, if you use this clever substitution, this whole expression P of C given X can be written as 1 over 1 plus e to the power of minus A. That's exactly equal to sigmoid of A. So it's sigmoid of this quantity, right? Although we said that the sigmoid in logistic regression comes about in discriminative problems, uh, in generative problems also, we can regard a similar sigmoid expression comes out. Only thing is, what are you taking a sigmoid of? The sigmoid we're taking off is logarithm of this ratio of the this product of these probabilities. And the numerator is one class, denominator is the other class. So it's an interesting substitution that takes the generative model also into the sigmoid area. So sigmoid is a very fundamental concept in machine learning. So this sigmoid is being shown here. If A goes from minus infinity to plus infinity, A is that quantity we just defined in the previous slide. That's a logarithm of P of X given C1 times PC1, like that. And the sigmoid has this S-shaped curve. And at 0, it has value 0.5. And as it goes to minus 5 or plus 5, it becomes 0 or 1. It's S-shaped or squashing function, it's referred to. It's squashing in that whatever be the input you give me of this A, it's a very large negative number or a very large positive number. It squashes it into a value between 0 and 1. And largely it goes into 1 or 0, and somewhere in between it has got a S-shape. Dotted line is a scaled probit function. There's another function called a probit function, which is a dotted blue line. It is nothing but a CDF, cumulative distribution function of a zero mean unit variance Gaussian. If you remember in probability distributions, you have what are called as density functions and distribution functions. And density functions like a normal density, it's called a Gaussian bell-shaped curve, where its cumulative distribution function will have a shape almost like sigmoid, right? It goes from 0 to 1. You're integrating from left to right of the PDF to define the CDF. All right. So Anyway, that's the sigmoid. So generalizations and special cases. So we just looked at what uh, a generative model looks like, and let's look at some more generalizations of that. So Softmax is a generalization of logistic sigmoid in that for k equal to 2, we have PC1 given x equal to sigmoid of A. We just saw that. For k greater than 2, we can use its generalization. PCK given x is written in the same way that we said earlier on. We have summation over all the classes. And that can be written by a clever substitution as exponential of AK or summation exponential of HA. How do you do that? Is where A is exactly this quantity. A is written in this way, and that is for k equal to 2. We are showing the expansion of that, and P of C1 given x exponential A1 or exponential A1 plus exponential A2. And from that, we are able to show that A is equal to this quantity. So we can, with some algebra, show that this quantity AK is defined by log of PCK, P of PC. So this is just one term here. This is the two-class term, and this is when we're just taking one term. And we can write this expression in this form. So we say that for k equal to 2, we have got this form in terms of sigmoid. For k equal greater than 2, we have this form, which we refer to as the softmax function. So this slide is a useful slide for you. If you want to say what is the generalization of sigmoid to any number of classes, and we say it is defined by this softmax, since it's a smooth max function, right? If AK is much greater than AJ for all J not equal to K, then PCK given X equal to 1 and 0 for the rest. So if one of them comes out to a very high probability and the others are small, a very high value, I should say, of this quantity, then one of them is 1, the rest are all zeros, so indicating that that particular term is maximum. So that's why it's referred to as softmax. Okay, we'll next see see that linear classifiers occur both in continuous and discrete cases as consequences of choosing specific forms of class conditional densities. So far in this discussion on generative models, there was nothing about linear classifier. We just said if you have probability distributions, then this is how the model is specified. So now we are saying if this distribution P of x given CK has some interesting forms, then we end up with linear classifiers. That's interesting. So this says if your distributions are Gaussian, so P of x given CK has this very complicated looking form, right? What is this? This is a probability density function associated with a continuous variable x is 1 over 2 pi to the d by 2, 1 over determinant of the covariance matrix to the power of half, and exponential minus half x minus mu transpose. This is the covariance matrix inverted, x minus mu, right? Inverting a covariance matrix, we just saw it can be done using standard inverse function or Moore-Penrose, A for Penrose, right? He got the Nobel Prize yesterday for physics. So anyway, that's Penrose. By the way, I was just looking him up. When did he come up with the Moore-Penrose inverse? Apparently, he came up with it as a student. He was an absolutely brilliant student. And his PhD was in mathematics. It was about tensors. He did his PhD 65 years ago. He's 89 right now. He did his PhD 60, even earlier. PhD was even earlier. He did the Moore-Penrose inverse, was published in 65 years ago. And he came up with his dissertation title says tensors, which is exactly what the software library you use in machine learning called TensorFlow, right? So his dissertation was about tensors, and then he came up with Moore-Penrose inverse, and then he went on to from mathematics to physics, and he got the Nobel Prize for for black hole theory, all right? Something to be inspired by. You start out with these basic mathematics, you make a contribution or something, move on to other things, physics or whatever, right? Okay. All right, now back to continuous inputs, Gaussians. So we have considered first the two-class case, and we are plugging in this expression into PC1 given X, two-class problem. And we can now write P of C1 given X as sigmoid, W transpose X. That looks like a logistic regression, except in this case, W consists of this quantity, sigma inverse mu1 minus mu2. W naught consists of this quantity, which involves the mu's of the two classes and the covariance matrix. Same covariance. We're assuming that the spread of the two distributions are the same. So same covariance matrix. So it says quadratic terms in X have cancelled due to common covariance matrices. There is no quadratic term. Quadratic comes about when you have X times X squared, right? There are X squared terms in the Gaussian, but those all get cancelled out. And the argument of the logistic sigmoid is a linear function of X. So this says, if you have two Gaussian distributed classes, like you have got this red peak and a blue peak over this two-dimensional space on the, which is the plane over here, and these look like pretty complicated things. Gaussians are bell-shaped curves, but it says if the two of them have the same kind of spread, right? They have the same shape, except their means are separated out. And it says, in which case, the decision boundary between the classes in this two-dimensional space is a straight line, defined by the values that we derived for W and W naught. And that's going to be defined by the difference between the two means and the covariance matrix sigma. All right, so those end up defining a linear classifier. So even if your two classes are Gaussians, it ends up having a linear decision boundary. And this is just a plot of the posterior P of C1 given X. This is X given CK. These are the two X given CKs. Together, they define the decision boundary. And the posterior is, if you just look at one class, the posterior PC1 given X, they plotted that. It's a form of a sigmoid, actually. It turns out P of C1. And the coloring given here is blue and red and purple in between. And it turns out to be a logistic sigmoid. It says the probability of blue class is high over here, and the probability of blue class is low, or the probability of red class is higher. It tends towards 1 there. So this is C1, one of the two classes. It goes between 1 here and 0 here. So this is an interesting observation that even though we are talking about a very basic definition of distributions, the classifier turns out to be linear. And we can talk about the continuous case with k greater than 2, which gets a little more complicated, but all this linearity holds here also. And so three-class case with Gaussian model, I guess, yeah, here we end up with both linear and quadratic decision boundaries. So we have one Gaussian plotted here, another Gaussian plotted here, another Gaussian plotted here. It's a three-class case. All three are Gaussian in this two-dimensional plane. And here, the boundary between just these two is linear. We just saw that between two Gaussians is going to be linear. But when you have a third Gaussian coming in, you're going to be defining a quadratic here. So these are the shapes of the boundaries between these classes. But I guess in this case, you see the covariance matrix is different for these two. So it is no longer linear. Between these two also, it's no longer linear. Because this one is spread in the horizontal way, this is spread in the vertical way. So that causes some kind of a quadratic effect coming into play. So the lesson to learn here is that a probabilistic classifier induces some kind of simple decision boundaries in the feature space, saying, okay, on this says if you fall on this side, probability is higher that it's a blue class, or on this side probability is higher, it's a green class, like that, So if you're going to be choosing it, just give me which class is the highest probability. You would simply say anything here is high in blue or high in red or high in green, and you just have a clear decision. But it's really a probabilistic classifier. It gives you a probability of the class. That's why they have some shades of blue and green and shades of red and blue and shades of red and green and so on here, right? All right. So this goes on to maximum likelihood solutions. So this says, well, if you had those Gaussians, this is what the boundaries look like. So once we have specified a parametric functional forms for the class conditional densities, we can determine their parameters together with prior probabilities using maximum likelihood. So if you say, look, this class is Gaussian, but I need to know its parameters. And what do you mean by parameters? Parameters would be, tell me what is the mean of the distribution. Tell me what is the covariance matrix of the distribution. We need that in order to plug it in to specify our decision boundaries, right? So we need that. It says, well, you could use maximum likelihood solution to determine the parameters. So maximum likelihood estimation, the Gaussian parameters, it's got all these equations and so on. The likelihood of a target T, okay, I guess we need to specify that. Data set is given xn Tn. We've got these values xn, and Tn denotes class 1, and Tn equal to 1 denotes class 1, and Tn equal to 0 denotes class 2. So we have a set of samples and a vector of n values if you have n samples, and they have values 1 or 0. The prior probabilities are being specified as PC1 equal to pi, PC2 equal to 1 minus pi, right? The two probabilities. And joint probabilities can then be written in this way. We're using n for normal over here. And then the likelihood of a set of observations T given the prior SPI, given mu's mu1, mu2, and covariance matrix sigma can be written as a product, assuming the samples are all independent, can be written as a likelihood function. So the problem is one of maximizing the likelihood. So we're saying what should be the values of the parameter? That's what we're interested in. What should be the parameter pi, mu1, mu2, sigma, the choice of which is going to make this as maximum, right? It's based on the observed samples n equal to 1 through n. So that's kind of clearly stating what do you mean by maximum likelihood solution. It involves first writing the likelihood function like this, and then trying to figure out its maximum. So here we are determining maximum likelihood for prior and for the means. For the prior probabilities, the log likelihood function that depends on pi are these terms. So there are some other terms which become 0, and they take a derivative with respect to pi, and then set it equal to 0, which tells us that the maximum likelihood parameters are n1 over n1 plus n2 for the first class, right? Which is kind of nice. It simply says, if you have so many samples for class 1 and so many samples for class 2, what is the probability of the prior probability of the two classes? It says, how many samples do you have for each class? N1, okay, N1 divided by N1 plus the other class. That is the prior probability. And similarly, estimates for the class means turns out setting up the likelihood function, and you maximize by taking its derivative with respect to 0, and you solve for it. And it comes out mu1 equal to 1 over n1 Tn x1. It simply says add the samples for each class, for the first class, and divide by n1 is going to be the mean for the mu1. So that's simple enough. Simply take all your samples, add them all up, divide by the number of samples you have. That's your mean. Similarly, that's the mean for the other. So it's a maximum likelihood solution to the parameters of a generative model where the distributions are Gaussian. And the more complicated one is maximum likelihood for the covariance matrix, shared covariance matrix. So we need to set up the expression again. and look at the likelihood function and take only terms that involve the covariance matrix, common covariance matrix. And then you end up figuring out, the weighted average of the two separate covariance matrices are being defined like this. And then you have S1 is defined as the covariance matrix of the first class, S2 is the covariance matrix of the second class, and that becomes a setting equal to 0, and that's what the solutions we get. Okay, so now you know how to solve the problem of, supposing I give you several distributions which are all Gaussian, they have some sharing of the covariance matrices and so on, and you want a generative solution to the problem, you would say, well, determine the distributions for each class. Using maximum likelihood, you can figure out the parameters. And using the distributions, you can construct the generative classifier, which figures out the probabilities for each class, which looks like either Sigmoid or Softmax as well, with even with a generative model. And that's a nature of a linear classifier. What about when you have discrete features? Say, look, my features are not continuous. They are discrete values. They take on, it's a binary picture, means the pixels are only 0 or 1. Or even if it is a grayscale image, a pixel can take 0 to 255. It's still discrete, right? It's not continuous. If you have 8 bits per pixel, then that's 0 to 255 discrete features. And so what is the solution? And do you really end up with a linear classifier using a generative model? Let's begin with assuming binary features. Xi belongs to 0, 1. So each feature can only be 0 or 1. With m inputs, so it's an m-dimensional input, distribution is a table of 2 to the power of m values. So we're talking about distributions can be specified by 2 to the power of n values. So we need a table of values. So how often does that combination of pixels occur? That's the probability. So that's the nature of the probability distribution. And we may do a simplifying assumption here. What if we assume the features are independent? So one pixel does not depend on the neighboring pixel. It's a very severe assumption because they do depend typically. But if you make that assumption, it becomes what's called as a naive Bayes assumption, in which case the joint probability distribution, class conditional distribution, which is what we have just been talking about, x given ck can be written in this form, mu to the x times 1 minus mu to the 1 minus x. This is the standard form of a Bernoulli distribution, like a coin toss, right? Coin toss can be written as, the distribution can be written as mu to the power of x and 1 minus mu to the power of 1 minus x, where mu is the probability of heads and x is 0 or 1, right? So corresponding to heads and tails. And so that's a Bernoulli. We're multiplying m times corresponding to all the features which are assumed to be independent, right? That's where the m is. And we are defining AK in the same way as we defined earlier on. And if we plug in log px given ck into it, it turns out to take on a form which is again linear in x. Okay, you got to take a look at it and say there is no nonlinearity. There's no x times x. X, and there's a 1 minus x here. So linear x. So similar results for discrete variables will take on more than two values, right? So this is saying that even with discrete features, the form of the classifier is again linear because these AKs are linear, and we need to plug it into its conclusion. Exponential family is going beyond Gaussian and discrete inputs. These ideas hold for a family of distribution called the exponential family, which is not just the Gaussian, but there are various other distributions that fall in the same family. You know, it is not Gaussian, but some variants of it. And how do you define those? The exponential family is defined as p of x given lambda k is equal to hx g lambda exponential. This is the very general form of an exponential family. And it's interesting to see what all distributions have that property. So this saying that even with exponential family, we have linear forms that can occur there also, which is kind of interesting. So summary of probabilistic linear classifiers, they are defined using logistic sigmoid and softmax functions. Continuous case with shared covariance, we get a linear function of input. Discrete case with independent features also results in linear functions. So these are all special cases. So you're going to have lines and planes when you have certain forms for the distributions, which is not too restrictive, independent discrete features or Gaussians with shared covariance matrix. Okay. All right, so let's then move on to probabilistic discriminative classifiers, which you already have a sense for what those are. I'm having a bit of difficulty here sharing this particular one. Let's see, share screen and okay, are you able to see this? Probabilistic discriminative models? Are you able to see? You're okay? All right, thanks, Mihir. Probabilistic discriminative models, fixed basis functions. So we just finished discussing probabilistic generative models. So the main lesson to be learned there is the probabilistic generative models go about modeling the probability distribution. All right. So keep in mind, machine learning is all applied statistics. So we're saying we are throwing a whole set of samples at you, and the generative method says, well, okay, then figure out the probability distribution of each class that you've got and use it to figure out what is the probability of any new input coming in, what class it belongs to, based on the strength of those distributions under each class. So that's the basic. That seems like a very basic intuitive idea that how would you make a decision on something? If you had a whole learning data, you would have learned from them and you would calculate what's the probability for each class. And that's what a generative model says. The clever thing is this discriminative models, which says, well, do we really have to learn everything about the distributions? Because that's a complicated matter to learn all the means and the covariance matrices of those distributions. Is that so much work involved in that? Can we directly somehow figure out what is the probability of each class without doing all the parameters of the distributions? Says, yes, it can be done. And that's exactly what logistic regression does. It simply says, well, figure out what is the importance of each of the features that you have input. Okay, and use that. If it's a two-class problem, importance for one class over the other. So you just figure that out, the importance, and that tells you what's the probability of that class, or one minus that will be the probability of the other class. And you can generalize that to multiple classes. So this is the intuition behind discriminative models. We just saw probabilistic generative models. I'm going to skip this slide. So the probabilistic discriminative models are alternative approach. Use the functional form of the generalized linear model explicitly. That generalized linear model we just saw, which involved magically converting the distributions to sigmoids. And then we determine its parameters using maximum likelihood. There is an efficient algorithm to find such solutions known as iterative reweighted least squares, IRLS, right? And there is an algorithm called IRLS, which hopefully we can do that today itself. And so the advantages of a discriminative model is fewer adaptive parameters. The generative model required lots of parameters. You have to figure out the means of the classes, and you have to figure out the covariance matrix. That's a pretty involved thing where you have to look at how dependent is each feature on each other feature. This doesn't require that many parameters. And you also get improved predictive performance when Px given Ck assumptions are poor approximation. If I didn't give you lots of samples for each class, and I just give you a very stingy handful of samples for each class, your distribution P of x given Ck is not going to be very good. In which case, for anything new coming in, you're not going to make such a good decision. So it kind of depends on how good your probability distribution is. Whereas this discriminative model, it takes advantage of whatever samples you got and looks at what is the competition between the two classes, and it figures that out. So this slide is just saying that you can go from the original input space x1, x2 to a feature space phi1, phi2. It's the reason it's being thrown in here is this method of logistic regression. You can say, well, how good is it? It's to draw a straight line. It says, don't worry, we can take your original input space. The original input space maybe had these red points like this, blue points on either side. So it's not linearly separable. I cannot draw a line that gives me blues and reds nicely separated. If I draw a circle around the red, that will be good. Falls inside the circle, it is red. Outside the circle, it is blue. I can do something like that. And what we are doing here is a nonlinear transformation of inputs using a vector of basis functions phi of x. We encountered basis functions before. So that can be mapped into a space, x1, x2 space, into a phi1, phi2 space, where you see the reds have been mapped over here and the blues have become two things here. Oh, wow, look at this. I can now draw a straight line between the reds and the blues, which is a linear classifier. So now we can apply logistic regression to this problem, saying, okay, it's a linearly separable problem. The original problem was not. How was it converted from this to this? Was basis functions are Gaussian with centers shown by crosses. So this phi1 and phi2 are Gaussian centered. You see, there's a green circle here. That's a contour of constant density of a Gaussian centered in the middle here, plus here. There's another Gaussian centered over here, which is this other circle. And so those are the two basis functions. So you have chosen this as a center, this is a center. There are only two basis functions. This is the original input was two features, x1, x2. So this is calculating the value for each point assigned by the basis functions, right? So each Gaussian gives you a certain value for each point, and that is a value mapped over here. So by just having some some basis functions, is able to map it into a linearly separable problem. So you see the power of these basis functions that was obtained. And how was it obtained? They just took the center of this of this red points, and they took the center of these blue points. I guess they could have had one more here, the third one, but these two were enough to give a linear separability. And so linear classifiers look like they're simplistic, but they can be pretty powerful using basis functions. So, but what is the limitation of fixed basis functions is that nonlinear transformations cannot remove overlap between classes. So when you make such a mapping, there can be overlap. They can even increase the overlap. Still, fixed nonlinear basis functions play an important role. All right, so that one solution to fixed basis functions is basis functions that adapt to data. So support vector machines use basis functions centered on the data points and select a fixed subset of them. So one approach is simply use basis functions, and another approach is to cleverly use basis functions based on what kind of data do you have. And it says, let's center them on each data point and then throw away all the data points that you somehow don't need. Okay, so that's this overview of discriminative models. I'm trying to find the next set of slides on discriminative models. Okay, oh, the next set of slides we've already seen, but I'll just quickly go over it. This is my lecture on logistic regression. You've already implemented it, and I went over some of it early on because you were going to do a project on it, but this is where it comes in. And let's look at it quickly, just to keep it in perspective. Okay, we are into the second part of probabilistic discriminative classifiers, logistic regression. We look at two-class problem. And the topics here are logistic sigmoid and logit functions, parameters in discriminative approach, determining logistic regression parameters, error function, gradient of error function, simple sequential algorithm example. You've done all of that for your project. And generative versus discriminative training, naive Bayes versus logistic regression. So in logistic regression, we have a probability of a class given a feature vector phi. This is, we replace X with phi, saying we don't use a d-dimensional feature vector, but we use an m-dimensional feature vector, cleverly chosen. And again, that is given by sigmoid of W transpose phi. And so anyway, there is some more interesting math detail here about logit and so on, which we don't need. And okay, this slide is an interesting one. Fewer parameters in linear discriminative model. The discriminative approach, logistic regression for m-dimensional feature space phi is m adjustable parameters. So you say you are using m basis functions, then we need m parameters. That's it. So we have to estimate m parameters from the data set. But if you took the generative approach based on Gaussians, let's say we're using again m features, then we have to generate the number of parameters, 2m parameters for the mean. So we need m parameters for specifying the mean of one class and m parameters for specifying the mean of the second class. Covariance matrix is where things get more complicated. M times m plus 1 over 2 parameters for a shared covariance matrix. It's an m by m matrix. Of course, it's a symmetric matrix. that one side of the diagonal is the same as the other side of the diagonal. So it's a m, so that is m times m plus 1 over 2 is the number of elements in such a matrix. And we need the two class priors, probability of class 1 and probability of class 2. So the total number of parameters is m times m plus 5 over 2. They just added these terms, 2m plus m times m plus 1 over 2 plus 2 gives you this expression here, which has got a quadratic term, m times m squared, which grows quadratically with m. If features are assumed independent, naive still needs m plus 3 parameters. Okay. So if you assume the features are all independent, then you need only order m plus 3, just like the discriminative approach needs m. So in machine learning, we worry about how much data do we have and how many parameters do we need to estimate. If you have lots of parameters to estimate, you need even more data points. So they're saying the discriminative method is not bad. It just uses as many parameters as the number of features in the input. Whereas the generative model is of the order of square of the number of parameters you need. So it's more complicated. That's why people prefer the discriminative model, saying I don't need to estimate that many parameters. And also I may not have that many samples because I need an order of m squared. M is the number of features. That many samples I don't have. You know, I had a friend once who, in the early days of drones, he was he was not a machine learning person, but he had a hobby, which is drones. He was flying drones, in his spare time, and he had a camera put into his drone, and he wanted to recognize, I don't know, street signs or something like that from, or maybe larger than the street sign sound seems like a really hard problem. Maybe the signs on a storefront, and recognize those characters and transmit it down to his app. And he was asking me, what should I do? I need to recognize some letters and numbers. What kind of classifier should I use to do that? And he ended up using logistic regression as the method to classify the characters so that he could the drone could read what is there on the sign. I don't know what he was trying to do. Maybe he wanted to land on a particular road. I don't know what he was trying to do by reading those signs. But so this was just a cut and dry thing. He just wanted, he was not necessarily a machine learning person or an AI person, but he just was playing around as a hobby to play with the drones, and he needed a solution to the problem, and this is what we ended up using, right? So this is a go-to method, simple method is this discriminative approach. And then you can say, well, you're going to need samples for all that, and how many samples do I need is his next question. Well, you got to capture all those samples of the kinds of numbers you have, and if it is what kind of resolution of your camera, and you got to square the number, okay, forget it. So a discriminative approach becomes a go-to method as opposed to a generative approach for such a solution. Okay, let's see, determining logistic regression parameters. We've seen this before. We set up a likelihood function. The Bernoulli comes to play here. And then we have these y's, it's P of C1 given phi, that's in the form of a sigmoid. And so we plug those things in. And by taking negative logarithm of this quantity, which is the likelihood, we get the cross entropy. This is how we end up cross entropy. Cross entropy is famous in machine learning and deep learning. People forget, where did that come from? It comes from setting up the likelihood function like this with the Bernoulli distribution, the simplest distribution. And you can set up a likelihood function like this, and you take a logarithm of that, which converts the summation into product into summation. You have a negative logarithm of that, and you're going to try and minimize this quantity with respect to the parameters. And there are, of course, some substitutions here. And we need to minimize, in order to minimize, we need to take the derivative and set that equal to 0. And this is talking a little bit about cross entropy and why it's called cross entropy. And I think I went over this already. Between two distributions, H of PQ, it's the Kullback-Leibler divergence of P and Q, and the entropy of P is called uh, the the cross entropy between the two, right? This is, so that is HPQ is T log y times 1 minus T log 1 minus y, where the Kullback-Leibler divergence is defined like this. These are all things, I mean, I don't want to go over all these detail from your implementation point of view and so on, but fundamental to your appreciation and understanding of machine learning is to know what these concepts are: entropy, cross entropy, Kullback-Leibler divergence between two distributions. These are all fundamental concepts that are going to be very useful. And so we're continuing that. We have the error function, and we go about saying, well, if that's your error function, the derivative of the error function looks like this. So it has a simple form. The derivative of the error function is yn minus tn times phi n. And this says take the difference between the output you're getting and what it should have been, and multiply it by the value of the feature vector. Error times feature vector. Add over all the samples is your derivative, right? So that's the derivative. And so that derivative is, so what are you going to do with the derivative? Well, the derivative is used in the gradient descent. It says Wt plus 1 equal to Wt minus eta derivative of E. So that is how you update the weight vector for logistic regression. And so this tells you what the derivative expression is for logistic regression. All right, I think I went over this slide also, a Python code for logistic regression, which is exactly what you implemented, I believe. So you are very familiar with it. Maybe you can tell me about it then. Me tell you, because you've actually implemented it just recently. Logistic regression code in Python, which you have seen already. And it says machine maximum likelihood solutions can overfit, and so we need to add a regularization term. So we have a regularization coming into play into the derivative here. Actually, it should come into the loss function itself, and it also shows up in the derivative. Example of two-class logistic regression: input data and initial weight. It is also talking about the second derivative here called the Hessian for the two-class case. The second derivative solution is a different solution, which we haven't gone over yet. So anyway, here is again summing logistic regression. There is numerous blogs and so on online. If you Google logistic regression, I found this one slide, putting it all together. What is logistic regression? Saying, okay, binary classification. This is a cat or it's not a cat, 1, 0. And logistic regression is a classification problem, is a linear regression plus sigmoid. Okay, it's an interesting viewpoint that this is how it is and so on. And this is gradient descent for that, putting it all together, x to y hat. It's a mini neural net is what's called as the sigmoid function is a mini neural net. There's only one node here. Okay. Anyway, so I want you to go away with at least one simple idea here, that is logistic regression, which is what your first project was. And Mihir encouraged you to work with different data sets and so on. And in real life, if you encounter some simple classification problem, maybe that's the go-to method, right? Okay, so let's see. Mihir, how are we doing? Shall I go over one more set of slides?
So we can start with the breakout sessions now.
You want to start now? Okay. All right, I think you got some good stuff. I don't want to keep on doing my thing because I think Mihir's stuff is really good. He's going to go over perceptrons. He told me that sounds really cool. I talked about this perceptron. That's another thing that Buffalo students should go away with. All right, you can always tell the world that you learned machine learning in the place where perceptrons were invented, and that was I mentioned to you, Rosenblatt invented perceptrons, and it didn't involve sigmoid. It involved a plus one minus one type of function. And Mehir said he was going to show you how the perceptron is implemented with plus one and minus one. And today we also talk about multi-layer perceptrons. Commonly you will encounter that term in deep learning and all, saying, okay, I'm using an MLP. What is MLP? Multi-layer perceptron. So then the question is, what is a multi-layer perceptron? Is it a several perceptrons stacked together, which is plus one minus one? Oh, no, no. It's one where we use activation functions like sigmoid or tanh or relu and so on. But the original perceptron only used plus one minus one, and that was its limitation. And they could not use proper gradient descent because you cannot take a gradient of a plus one minus one function, which is a discrete valued function. They moved to sigmoids, saying that's continuous. We can take a derivative and we do backprop. When we have many layers, we got to do backprop and chain rule of calculus and all that. All that could not be done with a simple perceptron. But anyway, it's good to know about perceptrons. And if you are a Buffalo branded MLP person, you can tell the world that you know about perceptrons, and that's you learned it at the place where they created it. Okay, all right, Meher, go for it. And should I need to convert you to become the host? I suppose. Yeah, I should change roles with you. Make host, and I'm going to